Now we're going to look at polar bonds and molecules, and the first thing we're going to do is roll back to discussing electronegativity. Electronegativity is the tendency of an atom to attract electrons to itself in a chemical bond. So if you recall the periodic table, if we put fluorine right here, this would be the noble gases, and francium way down in this corner. Fluorine is the most electronegative element, francium is the least. In a chemical bond, fluorine is going to attract electrons strongly to itself, francium will not. So polar bonds are caused by differences in electronegativity between the atoms. So let's take a look at an example here. We have chlorine, and if we have a chlorine molecule, where we have two chlorines bonded together. And I'm extending the bond just so that I can more easily illustrate what's going on with the electrons in the shared bond. Both chlorines are exactly identical. So it's like two people of equal strength pulling on a rope. They're both going to be attracting the electrons equally to themselves. So if we were to draw a cloud representing the electrons that are shared, the cloud would be shared symmetrically between the two chlorine atoms. So in a covalent bond where the electrons are shared equally, it's called a nonpolar bond. Now if it's a polar bond, the bonding electrons are shared unequally. So let's take a look at HCl. And again, I'm going to extend a single bond that is bonding the two atoms to more easily illustrate what is going on. In this case, chlorine is the more electronegative atom. So what happens is the electron cloud between these two atoms is attracted more strongly towards the chlorine than it is towards the hydrogen. So we end up with a distorted electron cloud, where electron density is being removed from the hydrogen and the chlorine is getting additional electron density. We can also indicate this by putting partial negative and positive charges. So this little symbols here that I'm drawing indicate partial positive and negative charges. So let's come down here. These are lowercase Greek deltas. And so we've got a delta negative or a delta positive. These are partial charges. Now there's a second way that we can indicate that. And let's just rewrite HCl. What we can do is we can draw a little arrow over this bond with a slash through it. And what this indicates is the electron density in this bond is being pulled more towards the chlorine than it is towards the hydrogen. Let me finish up with my lone pairs on the chlorine here. So we can also use dashed arrows, slashed arrows, which are going to point to the more electronegative element. So what we say here is this bond has been polarized. So we've got a polar covalent bond. Move down a little bit, and we'll talk some more about whether we classify a bond as nonpolar or polar depends on the electronegativity difference between the atoms. So here's a table that shows the electronegativity difference between the atoms. And we're skipping all the transition metals. So here's the groups 1, 2, 13, 14, 15, 16, 17. We're not including the noble gases because they don't have any electronegativity to speak with. Notice fluorine has the highest electronegativity, followed by oxygen, and then you've got nitrogen after that. So the rule of thumb is if the electronegativity difference falls between 0.0 and 0.4, we say it is a nonpolar covalent bond. So for example, hydrogen, we would have a difference of 0, because what we would take is we would take the electronegativity of hydrogen, subtract it from the electronegativity of hydrogen again, we would get a value of 0, so it is a nonpolar covalent bond. Let's look instead at hydrogen fluoride. There's fluoride, which has an electronegativity of 4.0. We would subtract 2.1, that's the electronegativity of hydrogen. We get a value of 1.9. Therefore, this is a polar covalent bond. If it's over 2.0, then we classify the bond as ionic. So, for example, sodium chloride, we would take the electronegativity of chloride, which is 3.0, and subtract the electronegativity of sodium, which is 0.9, and we get a value of 2.1. So at this point, we have an ionic bond. So what I want you to do here is to figure out what the electronegativity difference is between each one of these atoms, these molecules, and then determine if the bonds are nonpolar or polar. So we'll do CO2 together. In this case, you treat this as just one bond. Ignore that this is a double bond here. So you're going to have oxygen is the most electronegative, so you have 3.5. You're going to subtract carbon, so that's minus 2.5. You get a value of 1.0, so this one is a polar bond. Try these other three, and we'll go over the answers. For methane, carbon has a value of 2.5. Subtract 2.1 for the hydrogen, it's 0.4, which means this is considered a nonpolar bond. Carbon tetrafluoride is considered a polar bond, as you have an electronegativity difference of 1.5. Nitrogen trichloride would be nonpolar for each of the NCl bonds, as they have identical electronegativities. And finally, potassium chloride, as expected, comes out as an ionic bond because we have an electronegativity difference of 2.2.